Hello, everybody. I wanted to run you through what's required for the first lab for this completely online DLON BSC 1025 for Nutrition and Drugs course. So if you take a look at what we have on Canvas, you should now see the main page for your course. Hopefully by this point, although I haven't had many questions come my way, you've had a chance then to go through and read through everything, to ask any question you might have, like on the syllabus, and to start reading your chapters. As I've noted, both on the front page, it's right there, as well as when you go to the announcements, you should be checking these every single day. I've already had a few up here for you, as you can see, including the orientation issue to the class. This more or less runs you through everything in the course, not just what's there, but how to get started, and an orientation video. You can click on that video here. I still recommend you open up a new tab because it just seems to work a little bit better. And then you don't need to hear myself talk about myself. It's interesting, breaking in the fourth wall yet, to listen to everything I had to say about your syllabus and how it sort of works. It's all here for you, especially not just being fully online, but with this also being a C class, 1025C. That means combination lecture lab. There's a lot going on. So while I try to be as explicit and thorough in the syllabus, and I've gotten perfectly great feedback on the syllabus, it's hard to make sure everyone's sort of on the same page. So that's why I put up this video, but you can obviously access it here, or if you wish, I specifically made light of it in the orientation announcement. It's the same thing. I just wanted to make sure everybody saw it. So if you took a look at that, and again, I've had one or two questions, but nothing that I don't have to amend or go back in and redo anything in the little video for you. So making sure you're following with the web page, then back to the main page. In this case, because it's a lab, go to your files. And when you click on the files, you get this. You should already be familiar with this because of anything else. That's where your syllabus is. And I had that whole video there showing you everything about that. And of course, your lectures. As I said, you need to read the chapter and then go to my summary posted lecture notes. But since this is dealing with lab, obviously it's here. As I mentioned, in C courses, there's more lecture than lab. And these are the labs that I understand my colleagues are doing as well. So you're getting the same thing as everyone else, as far as I'm aware of. So in this case, because as it lists in your tentative schedule, we're doing the first lab. In fact, we can take a look at that. Okay, get it to open up. So go down to the tentative schedule. Of course, it tells you everything, including when your exams are. So remember, I gave you a suggestion when to do the first lab. As I explained in the orientation video, you can do these whenever you like. It's a C class. And in that case, it's a DLON C class. So in this case, especially being a DLON class, it's okay. And nothing is due. None of the homework is due until the 4th of October. That's when your first exam is, as clearly shown here in your syllabus. And in that case, I just suggested doing it on the 15th. But hey, if you do it on the 20th or you do it October 1st, it doesn't matter because you're doing it on your own. This video then is just meant to help you. So for that first lab, you would have said, oh yeah, I've got to do lab 1 and later, of course, lab 2 for the first exam. I'll do my best to put up a video on lab 2 as well. You would click on lab 1 in the files links. Let's go back to that. There's your labs. You click on exercise 1, that's lab 1, and you get this. Now, it's up to you when you want to do this. I do not know if you've had time to read this. I've had one student ask about it, so I know people are getting into it as it notes in the tentative schedule. That's great. This is just meant to help you further along. And there is one change to the procedure here, a significant one, that I want to make note of, because this is going from a lab given on campus and trying to do it now fully online. That's really hard to do, by the way, to rework a fully fleshed out working lab that was built to do in person on campus. You would be in groups, working in groups, that kind of idea, and to do it by yourself at home, especially when something like mathematics are involved. So I'm going to show you how to do the procedure once I get down to the bottom of this. First and foremost, just reading over what it is, this lab relates more to your second chapter. And you can see in the second chapter, that's when they formally bring up the scientific method. The scientific method is something you've probably seen since like elementary school. It's a way in which scientists, although other fields as well, can go about understanding the world around them and then setting up procedures to test the world around them. This always starts with observations. That is the most critical tool of a scientist, really. And frankly speaking, it's the most critical skill and therefore tool of a human, paying attention. they train that. That's not an innate skill for a lot of people. Logic and observational skills are not really human innate traits. Again, some people are better than others, but they train this to you as scientists. As you go through your high school, yes, when I went to high school, I was taking a lot of science classes because I had a feel I was going that way for my graduate studies and my undergraduates, and that's what I wanted to do. But when you get to college and now you're a science major, they really do try to focus in on this kind of thing to get you to pay attention. To us then, minutia is everything. And again, you can use that in everyday world. My wife lamentably was in a car accident and her car was drivable, but I wasn't there. She was going to work, that kind of idea. So I wasn't there. When she got back, I told her when she called me on the phone saying, look, I don't think you should go to work today. I think you should bring your car home because it's drivable, but you can take my car, or you could call in today because you were in a legitimate car accident. Nope, I'm fine. I'm fine. The car is fine. Everything's good. We're going to go. Okay. She came home. Great. Quite literally like the next day, we had to take the car in to be dealt with because she was not at fault. Somebody hit her. So we took it to the place that person's insurance, again, working with our insurance, said you had to go. Sure enough, on the way there, I'm driving because now we drive. So I'm driving there. And as we're there, as we're on our way, it's like halfway there. I know it's really hard to see, but I know there's like, look at a little white puff coming out the edge of the hood. I couldn't quite tell though, because the road we were on is like down Maybury. It's kind of light pavement when we were, so I couldn't quite tell, but it caught my attention. And so I'm driving, I'm paying attention to that. I'm paying attention to what's going on around me. Did I see that? Did I see a white puff? Sure enough, not too long later, another white puff. It's hard to see, but it's there. And then I said, hey, look, I think your car is really having problems. You didn't realize this. And she may not have. Maybe as she was driving, something else happened, that the accident damaged the car and it took a little bit to show the symptom. So I said, I think you have a bigger problem here than you realize. She goes, no, my car's fine. No, look, that's watch. And she watches and watches. Sure enough, there it is again, because she's really paying attention. Oh, maybe you're right. And then sure enough, in the like 3-mile drive we took from our home to where the insurance company said to take the car, now you can clearly see that white stuff coming out. So it's like, wow, you really had to kind of pay attention to see that. And now we knew as we're rolling up to this place to deal with her car from somebody else hitting her, now we know there's a much more significant issue on our hands. And they have to deal with that. Geico, Progressive, and all these insurance companies that are involved with this have to deal with that. Okay, paying attention. And I'm like, phew, I'm glad nothing happened to you when you went to work. So again, paying attention. That's a critical skill. Observations. It does not matter if you're doing this in regards to science. This is something you need to do every moment of your life. If I may, my wife, by the way, knows I talk about her stuff. It's nothing inappropriate. But I got kind of teased by her by this. She's doing something, or I see something, or I hear something. Oh my God, did you see that? You actually heard that? Yes, I did. Even if I'm not looking at it, not paying attention that it looks like I'm seeing or hearing it, I am still. I try my best to pay attention to what goes on around me. Now, I'm human like anybody else. Some days are better than others, but I try my best because I've been trained to do it. Now it's kind of like automatic. And it kind of annoys her. Oh, you actually heard that? Yep, I heard it. Because it was trained in us. This is not an innate skill. And that's why this starts here. Not just to train our scientists to pay attention, but when they do research, so they don't find out, say, on year 2 of 5-year project, they screwed up because they missed something. And all these years worth of data become nonsensical. It's not viable work. We want to be careful of these guys. There's nothing really wrong with an anecdote. They're great. And they might give you direction or something, but it's just an anecdote. It's just like I heard, I saw one thing, maybe one test did this, and that's not enough for science. It gives you an idea. You paid attention, you saw something, maybe it was a one-off, but it gave you an avenue. Ah, that was interesting. Let's set up an experiment based on my observations, maybe based on the anecdote, to see if it is truly a repeatable phenomenon. That's what this is about. And really the job of a scientist is no different than just any other field. It's to understand the world around us, who we are, our place, not just in the planet, but in the solar system and in the galaxy and the wider universe. Who and what we are. What is natural phenomenon? That's what science investigates. We just have a very specific way to go about it. So we pay attention. That's the very first thing. We observe the phenomenon. If it's a phenomenon that's only observable to you and to nobody else, we might want to think about that. And then once we've observed it, we have an idea, I think this is what's going on. Then we might do preliminary examinations to kind of get a better feel of it. It's not the true test. We're just kind of testing our way into it, if I can phrase it that way. And we're trying to design this. A hypothesis if I may phrase it this way, is an educated guess, but I strongly emphasize the educated. It's based on something. Your past work, somebody else's past work, past published research, it's based on something. And if no one's ever done research on it before, you're that cutting edge, fine. It's still based on something. Your past observations, your past work, it's based on something. It's an educated, testable idea. Now, it is not a theory. That is something that's really quite troubling in common vernacular, like everyday vernacular, particularly in movies. I see this regularly in movies. Something going on the screen, and they'll say, hey, what's going on? What's your theory? Oh, that's not a theory. That's a hypothesis. Because what's a theory? A theory is a well-established hypothesis. We're just after the hypothesis. And so you set this up. And when you set up a hypothesis, your educated guess. In statistics, you usually set up two things. You can see one right there, the HO. That's your null hypothesis. This is the I think this is what's going on idea. But kind of like the other side of the coin, we generally have what's known as an HA, an alternative hypothesis. So if this is like an if-then, if this is happening, then that's why it's going to occur. This is the answer. Then we have the other side. Well, if it's not this, then maybe it's that. The HO and the HA. This lab was really only asking you to do the HO, set up a hypothesis to test something. But I would like for you to be cognizant, at least, that there's often listed the HA. If it wasn't this idea, then maybe it's this idea. Two sides of that coin. And even though this lab was after quantitative issues, there's a student's T at the bottom of this. That doesn't take away from qualitative issues. Observational, again, observational science has been around for centuries. And in fact, the area I went to my master's was ecology. It was very common to do observational studies. It wasn't until like the 1960s, which is of course before my time, but until the 1960s that people really started to like branch out into making ecology a testable field. That is not easy to do, by the way. It's a really tough science to work with. Fascinating, which is why I went into it, but tough. And so almost by default, while we love our mathematics, sometimes we kind of disregard the qualitative, and you shouldn't. Both are equally important. Now, this lab does use qualitative, and you're watching things, sure you can, but they're focusing on the mathematics, quantitative. That's statistics again. Stats is an amazing field, amazing, but it's almost like a bit of a magical mathematics in that it's sort of like, hey, I've got this data set. What is the data set telling me? That's the point of it. Looking for meaning in your data. Is there a statistically significant meaning to this data that you collected? But here's kind of the magic. Based on what you do with the stats, it's like you can get it to say whatever you want, and that can be a problem. One of the hardest things often in statistics is not running the statistic. It's figuring out what is the right statistic to employ in this situation. So you're not missing the point or fudging your data, which I'm sure you would never do, nothing like that. So it's challenging. And if I may, politics kind of comes up here. Every time I get into this subject, I think about politics. And in no way am I trying to look ill on politics at all. It's a field, and I'll leave it to you to what you think about politics. But why is it you see that two politicians can get up and have sort of the same data set and yet say exactly opposite things? How in the world did that happen? Because it's just a data set. And so we're trying to use statistics properly. And we often always use mathematics to deal with the data set. And that's why this lab kind of went that way. What can you see? What conclusions can you draw from the data you collected? Which is why, again, there's a student's T on this. Now, as I noted here, and I have this in my syllabus even, I even mentioned this, things like websites, magazines, newspapers, pamphlets, blogs, that's like tertiary information. It's not rigorous enough. I believe that wasn't here. I don't know if it says in here, but it's not rigorous enough to be taken seriously. That's the way to put it. Because it didn't go through peer review. Frankly, let's take a website. Frankly speaking, anybody can put up a website and say whatever they want on it. My last name is actually Stevens of the mom's side of the family. So I'll use me as an example. Mr. Stevens builds that website and says this on it. Does that mean Mr. Stevens is right? No. Mr. Stevens, in this case, I'm talking about myself. I can say whatever I want on that site. Now, granted, there's things like slander and libel and all sorts of things that come up there. Don't do that. But still, I mean, if I'm talking about cells and I say this is what cells are doing, does that mean I'm right? No, it doesn't. It's Mr. Stevens' idea on his website about cell biology. So you really need to be careful with this. It's not vetted in any way. Now, granted, I put up that website and I say what I want about cells. Someone else could chime in if I have like comments available and say, hey, that's not true. It's this. I guess you could say that's kind of being vetted, but that doesn't mean I'm ever going to change my website. So because it's sort of that situation, we never really view these things as serious. We never view it as rigorous enough to be taken seriously. Scientific journals are. These are peer reviewed. Here's how it's supposed to work. You go out, you do your research, you collect your data, maybe you run your stats, you get meaning to your data, and you say to yourself, yes, I think this is worthy of more consideration by the scientific community. So I'm going to try to publish. And then based on the data you did, maybe I went out and you can see some fish in my background here. Maybe I went out and did research on ichthyes. I had a buddy of mine. I worked at the Waikiki Aquarium for a number of years. And while I was volunteering there during my undergrad, one of my colleagues was actually doing like offshore deep sea shark biology, particularly he was working on oceanic whitetips. This is fantastic research. And so he was doing endocrinology work on them. He would bring them in, do blood work on them, and then look to see what's kind of happening in the groups in these deep sea environments. And so he decided, based on the data he had, that the stats look good, that this is worthy of publication. He went out and he found a journal that related to his data. So again, maybe I'm doing something like that. Maybe I want to publish in the Journal of Marine Biology and Ecology. So I'll go to that journal. Almost first thing in there is like instruction to author. So I have to read the instructions to author and find out, here's how they want you to format your paper. Right? I've got to structure everything based on what they want. Send it in. Here's what's supposed to happen. They're supposed to take your name off the paper and then send your paper out to like 3 to 5 scientists whose job it is to destroy your research. They don't know who you are, your name's off the paper, so they don't know who did this, which allows them to hopefully unbiasedly look at the data and say, it's good, it's not good. We might publish it because of, we're not going to be publishing it because of. That's their job. It's painful, yeah, but that's their job. And then they send it back to the publisher with recommendations. We love it, publish it, which rarely happens on a one-off. Or, it's good, it's got merit. But they need to do some things to maybe consider having it published in your journal. Or 3, no, it's not for us, go find another journal or, redo the research, that kind of idea. It's painful. It is a professionally painful thing to do. You can spend years of your life doing the research, only people that reject you out. It happens. But the point of it, of course, is so that when you go and read a scientific journal, when you go to USF and you pull a journal off the shelf, or you find something online that's in a mainstream journal, it's good science. That doesn't mean it always happens. I teach my second semester major biology students how to approach scientific literature, how to read published papers. And I warn them, just because it's published does not mean it's good science. Sometimes things get through. And so even when it's on a journal and you pull it off the shelf and you read it, you still must read it critically. Once it's in the scientific community's hands, actually, our job is to destroy the research. Because again, the idea is the same, to push science, push it in a good direction. That's how science works. That's what a scientific journal is doing. That's not really what a website, a newspaper, a magazine, a pamphlet, that's not what they're up to. I would hope magazines and newspapers are vetted. I mean, I can't speak to any one newspaper magazine. I'm not involved in that, but I would hope they are. But when I pick up a newspaper, especially a newspaper, I took courses in how journalism work. And they made it very clear to us that newspapers are written kind of like at a 6th grade level. Nothing wrong with that. I asked why, and they said, well, because we want to have it as available to the wider audience. That's never going to work in a scientific journal. So it's just a different audience. Even though I'd hope the information in it is vetted. Magazines, same deal. Some magazines are more rigorous than others. Some are more challenging to read than others, but I don't consider them nearly as rigorous, again, as a journal, a scientific journal. So you need to be really careful about that. And that's what we're doing here. That's what we do as scientists. Set up the procedure, do the scientific method, observe, hypothesize, test, collect your data, analyze your data through things like statistics, and then maybe publish. The point of this lab is to give you exercise on the scientific method. That's the whole point of this. We're going to have you try and set up an experiment, hypothesize what the idea is, but not run it. Just set it up and see, hey, this is something I could test, just so you get a little more experience with working with the method. So your author then goes and gives you a lot of examples of things that could be done. So this is a nutrition class. It makes sense that they're talking about nutritional issues. That's perfectly fine. So they're talking about, say, foods, for example, in here. Okay, I don't know where they started necessarily, but they're talking about foods in here and how foods can be linked to disease. Absolutely. As I say in my lecture, so if you're taking this D-Live C, you would have had live lectures with me. It would be just like this. I sit down, you sit down, we have a lecture. I'm talking about all the material. You can ask questions real time. I actually really like the D-Live C. I've got nothing wrong with the D-Lons. That's perfectly fine. They serve a very specific purpose, and that's great. But it's like being on campus and you have a discussion going on. And so we would talk about, how you would set up these procedures and how diet is really important. I would say things like, yeah, never underestimate the power of your diet, ever. I would make a comment like that. It's very important. And so like salmon, I am technically a pesca-vegetarian, kind of a loose one, but technically am. I do not like fish though, which is one reason I like the diet, because there's some flexibility in it. But they might test something like this, like, can fish be healthy for you? Or maybe the compounds you get in fish, who knows, like alpha tocopherol. Is it only from the fish source that is good, or can you take it in supplemental form? You would try to set up an experiment to test something that you might have in your diet and how that impacts you. Is it first off healthy, that thing? And then what context is it? Do you need it in the regular source? Do you need it in a supplement? Do supplements even work? There's a lot of ways you can go about it to try to deal with things like disease, pathologies. Okay. So notice how they're saying independent and dependent variables. Yeah. If you set up an XY Cartesian plane and you look at that, usually the x-axis is the independent axis. It's not being influenced by what's going on. So it's often then like time is put on the x-axis because whatever's happening is happening during the flow of time. But time itself is not being affected by the events going on. So maybe you look at things like you've been eating dark chocolate for a long time. Okay, so the time is 6 months. 6 months is not affected by the fact that you were eating dark chocolate. Time is not affected by the fact that you're eating dark chocolate. But as you eat dark chocolate over the 6 months, maybe cardiovascular differences, disease issues are being affected. Maybe rates of coronary artery disease decrease over X amount of time, 6 months, a year, 2 years, 5 years, as people include into their diet something like salmon or something like dark chocolate. A side note on dark chocolate, research does indicate that dark chocolate can be very useful to you, can be almost medicinal in a way, but there's a qualifier there. It is 70% cocoa or greater chocolate content, so cocoa content. Something like, and this is not meant to in any way again degrade Hershey's, but something like Hershey's dark chocolate, that would not count. That's just candy. You need to go like to Publix or something like that and find a bar of chocolate that's 70% or higher. And the greater the cocoa content, the more bitter it becomes. So a lot of humans don't like true dark chocolate, but the true dark chocolate has been connected to things like lowering cases of heart attacks, lowering the risk of heart attacks. So cardiovascular function has been affected by it. Who would have thought chocolate could do that? Yeah? The right form and the right amounts. I also know I do eat chocolate. It's taken me a long time to get used to it because it is bitter. But when I do that, I only have dark chocolate maybe once or twice a week. That's probably more than enough to help with these kind of issues. And on top of that, it's high calories. So you do need to be a bit careful there. So it's just testing. In this case, the independent variable would have been time. The dependent variable would have been effects of dark chocolate on coronary artery disease. That kind of idea. So notice how they start with the observational studies. Maybe doctors over time had noted that when they query their patients, maybe they had cardiovascular issues and now they're getting better. Hey, what's changed? What's going on? Oh, I changed my diet. Really? What'd you do? Well, I did this and I excluded that and I included this. Interesting. Now, granted, a patient, that'd be more like an anecdote. This doctor's seeing it over 10 patients, 20 patients. Wait a minute, a common theme here is dark chocolate. That's interesting. The doctor paid attention and all of these patients coming in and all these discussions that there was a common theme there. And so they set up their experiment to test that. Cool. So a lot of ways you can do this. Here they're talking more fish, tilapia fine versus salmon. Maybe you can test then tilapia versus salmon and its effect on coronary artery disease. There's a lot of things you can do with that. And so they ask questions. What does salmon have that's lacking in tilapia? Perfectly valid question. You were comparing and contrasting salmon. Does a component of salmon offer protection against coronary artery disease, or is there a trigger for a disease in the tilapia that's lacking in salmon? It's a great question. And I like how the author put, is salmon good and tilapia bad? Good questions. These are the kind of things you would test. Maybe the answer is no, they're perfectly fine, but they do different things in the body. Or maybe, yeah, tilapia has a downside to it that's not seen in salmon. Who knows? Until you set up the experiment and formally test it. And that's important in science. I hear people criticize science for that. Oh my gosh, you spent all that time and all that money. Why did you do that? It's apparent, right? You should have known the answer. Why did you waste your time? Because it wasn't apparent. Until we sit down and actually test it, we don't know. Science is mute on an issue it hasn't tested. And so you do the experiment only to find out, wow, I got answers that I weren't expecting. What do you know? So the author's correct to note to control your variables. Yeah, don't add in too many confounding factors because it makes it difficult to figure out what's going on. And there's a phrase here, and I've seen this before, that the simplest experiments are often the better ones because it takes out a lot of these confounding factors. That being said, just because it's a simple experiment does not mean it's accurately reflecting what's going on. We have to be cognizant on our experimental design and to keep our understanding based on what we tested and what the data said within this experiment. Extrapolation could be fine, but you better be careful there. Maybe though it leads you to another experiment, a more broad experiment, or a different path in the experiment. So yeah, try to control it. Try to not overdo it. It means even in this work, you don't need to set up some incredibly elaborate experiment for me and say, wow, look at me, look what I did. could be entirely nonsensical. Complexity doesn't mean good. Got to be careful here. But it takes time. It's not easy to set up experimentation issues. So what we're looking for here in this lab is thought process. Give it a shot. I'm not going to read these labs and say, oh my God, you thought that? Of course, I would never do that to you. Just try. That's why I said even in the syllabus, I grade on effort. I do. I really want you to give it a college try. Tests are a little bit different game, mind you. In there, you better get them right, or your test didn't go so well. But in homework, that's meant to get you to understand the information and get prepared for those exams. So we do like lowering confounding factors. If you're looking for a test group, for example, here, for example, if you're doing humans and you're testing foodstuffs in humans, you don't want to have 5,000 different humans because then it becomes really difficult to understand. Well, wait a minute. We had age groups from 18 to 90. Okay. And then we had both males and females. Okay, that's fine. But then we had some with chronic illnesses and some without chronic illnesses, and some had diabetes and some had cancer, some had dementia. It becomes really difficult to kind of know exactly what's going on. So yeah, being uniform is kind of nice. It doesn't mean you can't have different people in the group. You just got to be specific. Like I did 18 to 24-year-olds, or I want to test people who are only in their 40s, or maybe senior citizens, maybe 60s, 70s, 80s. Or I only chose males, or I chose females for some reason, or I only chose something specific in sizing, maybe only people who are overweight. Okay. You just got to be clear on why you set it up that way and then try to run the right stat. Okay, so for the report itself, now here's the biggest thing. If you're at the Mabry campus, they would wanted you to actually run this experiment as a group to kind of figure out what you're going to do and figure out a way to test it. They'll go off for the next few weeks and test it, and then we can come together and start working on the stats. You're by yourself at home. I do not know where you are. I've never met anybody. I may never meet anybody. That's okay. Hello, you know who I am, but unless you set up a Teams appointment, I'll probably never formally meet you. That's okay. I mean, it's just the DLON is very impersonal. No worries. I'm still a very communicative professor, so if you want to talk to me, set up those appointments. It's no worries at all. And in that case, then it felt a little bit incorrect for me to expect you to go out, try to figure out how to do this on your own anyhow, which is not easy, and then find 20 people to work with. Is your friend pool that big? Mine's not. I don't know what that means to me, but mine's not. So it seemed a little bit difficult. So I want you to do this, if I may use the colloquial phrasing, theoretically. I don't want you to actually go out and test anything. I want you to get more comfortable. And then for me, the point of the lab is to understand this. This is a great slide by your author in your textbook. Understanding why we have this method. What is the method? What is the parts of the method? And then how to employ it as scientists. I mean, here are the parts again: observation, hypotheses, testing. So you're doing designs, analyzing through mathematics, deciding if you want to publish. It's everything I just talked about in this lab. That to me is the point of the lab. It's great if you actually do experimentation. And again, at the Mabry campus, if we were there live together, we would try to do something, making it as safe and hopefully enjoyable as possible. There's no reason why science can't be enjoyable, right? But again, I think in this case, because you're most likely like at home by yourself, I'm not expecting you to do it. We're going to be doing, again, the colloquial, theoretically design something for me. You don't have to test it. So, as is correct, I really like the author who noted this. Before you ever do anything, you should always read. Get an idea what's going on. When I give live lectures, when I'm on campus, I tell my students the most critical thing you can do before you walk in that door, or you sit down in front of a camera before a lecture, is read before you come in. Have that chapter read. Whatever I'm talking about that day, which is in your tentative schedule, that's what I would have said to them. Read that chapter before you walk in the door. You don't need to understand everything. You just have to have a sense of what's going on. So when I get up there and I go my 1,000 miles an hour, because I've been lecturing on this stuff for the last 20 years, you know where I'm going with it. Same with the lab. Before you ever walk in the door to a lab, you should have read the lab beforehand. You don't need to understand everything. You want to have a general idea what's going on so that you come in. If anything else, you're safe. Labs are inherently dangerous places. So like I'm even showing you, it says, correctly so, you should have read the discussion in scientific method in your textbook. Absolutely. Now I'm showing you the summaries. This is my posted PowerPoint notes. But even like I said, when I went over the syllabus, read the book first, then go to the PowerPoint notes. Yeah, do that. And then think about your life. Before you set up this experiment, you've already been doing, I'm guessing 20, 30, 40 years of paying attention. I hope. I'm sure someone in there in the last 20, 30, 40 years of your life, you've had a diet. Yeah. Have you ever eaten? Ever? One thing on that, if I may say, it's not really a good idea to say something like, I'm going to change my diet. No, actually, let me rephrase that. I'm going to start my diet. Really? You're going to start a diet? Because if you're just going to start diet, that means I've never eaten before, I'm going to start eating. It is better to say, I'm going to change my diet. Because I'm pretty sure in the last 20, 30, 40 years, you've been eating. So you already have a diet. You're not going to start the diet, you're going to change it. And so pay attention to what your diet has been. Maybe recently, maybe in the last 20 years, who knows, whatever you want to do, which means you've already been collecting observations. And maybe you've noticed something cool. Like, yeah, wow, I really like this. Or I feel really bad after I eat bread. Or is it true that resveratrol, found in like red grapes, is good for you? Whatever. Maybe you read an article on dark chocolate, whatever it may be. So you can set up a hypothesis. This does not have to be based on anything way out of left field that you've never heard before. And you're like, wow, I really don't know how to go about it because I don't even know what I'm talking about. Welcome to being human. Think about what's happened. And then this is right. This is your challenge. Try and think about what's going on with like food and what that means to not just you, but the bigger group. Now, if I may, in the idea of evolutionary theory, Charles Darwin was clear on this. Individuals don't evolve, populations do. So maybe in some groups you're seeing things that other groups aren't. I'll use myself as an example. I'm not trying to be narcissistic in any way, but I talk about myself a lot in class. Because of any one thing, I can't get sued talking about myself. I'm not going to sue myself. So there's a reason why I talk about myself a lot in class. It's a safety issue, anything else. So my mom's side of the family is Ulster Scot, and my dad's side of the family is Russian. Taking my mom's side of the family, the Ulster Scot, I have Scottish, English, Irish, Welsh. I have got the whole shebang pretty much in me. It's primarily Scottish and English, Ulster Scot. Here in the Americas, it's called Scots-Irish. Fine, but better phrasing is Ulster Scot. And so with particularly the Scottish and the Irish, and of those groups, and that DNA in me, particularly the Irish, there's a bit of an issue there. The Irish have the highest rates of celiac disease on the planet. A lot of people can get that, and you don't have to be Irish and still get it. But that's the highest rates on the planet. It runs about 25% of the population. So because of that, even though I have far more Scottish DNA than Irish, I have to be on guard for celiacs. So things like maybe wheat may not go so well. Too bad, because I'm Western and I really like bread. So too bad. I have to be careful of it. So maybe that's something that would be particular. Why is it that celiacs is really high in some groups? So when I do my yearly physicals, and if I start noting physiological problems, like I start to connect, you know what, when I eat bread, I start getting tummy issues not long after, maybe a couple of hours after. Maybe something's up. Well, because of research that's been done on populations to know that because of my genetic profile, I am at heightened risk to celiac disease, and I've tested it, I am at heightened risk of it. It's something to be cognizant of. So research has already been done to know, yeah, Mr. Jacobson, which again, the other from my family is Stevens. Yeah, Mr. Stevens, maybe you've developed celiacs. Maybe now they've gotten into your 40s. Maybe when you get to your 50s or 60s, celiacs begins to show up. And now you can't have bread anymore. So something's happening. And that's what you want to test. In this experimentation issue, setting up a design, try to think of why you want to test something. Maybe you're of a certain group, and that group is known to have issues. And so maybe you want to investigate that. Great. Try to think of something that you can test. That's all this is about. So you're going to do a testable hypothesis. But like I said a few minutes ago, I don't expect you to actually run the experiment. You're not with us at Emory campus. You don't have colleagues to work with. I would have broken you into groups, and you'd be working with like 4 or 5 other people. And you would come together as a group to test something, and then you would decide how you want to do it, safety-wise, that kind of idea. Safety is always important. So theoretically, just kind of decide what you want to do. And yes, as you set up that hypothetical experiment, you definitely want to be cognizant of that. So your author goes and gives you examples of what you could do. I already talked about the null hypothesis. That's at HO at the beginning of this lab. There it is right there. So they give you different examples. I've already been giving you examples as we go through. So here they're talking about smoking, okay? Wherever it went, I think I saw smoking. Yep, there it is, smoking. And there's connecting smoking with like resting heart rate, the kind of idea. Or they were dealing with BMIs. Okay, so with the BMI, it's got kind of like a love-hate relationship. For me, as a scientist, I kind of look at the BMI as a rough-headed rule, because BMIs can be misleading. So in that case, maybe you want to look into that, and you want to set up an experiment to test the efficacy of BMIs. They're just giving you examples here. I don't care what you set up, because this is all hypothetical. You're not going to be testing anything. So whatever you decide, you can still run it by me. They know that's a good idea to run it by the teacher. I don't care. If you want to, great. If you don't, you guys are adults, you're college students. I know you're educated. You can do this. But if you have any questions for me, as I've been saying since the beginning of this course, you're welcome to ask whatever you like. Just send me an email, make a Teams appointment. We'll talk about the subject matter. Now, here's where I was deviating. You do not need to go and find 20 individuals. If you want to, I guess you can, but I don't think you should. And if you ever did anything, you better make sure it's safe. So if you're going to do anything like that, you need to run it by me. It's that simple. If you're going to go and actually do something, which I'm saying you don't need to do, run it by me. Don't ever just do it on your own. So like I said at the beginning, in this lab, you will not be testing anything. So you're setting up something hypothetical. So don't worry about this. You don't need to worry about finding 20 people. You don't need to worry about separating 10 in this group and 10 in that group. You don't need to because you won't be doing it. So what you're going to be doing is really down here in the what to submit. What I would like for you to do is try to figure out, first off, a subject area. I want to test dark chocolate. Fine. And then try to set up a hypothesis based on past readings. Just go and you have a Gordon rule in this class anyhow. So go and look up a few papers. You just plug in, I don't know, you can go to Google. Let's try this. Let's do it together. You don't have to use this, just showing an example. So let's say health effects of dark chocolate. Chocolate. It always helps to be able to spell right, yeah? There we go. Okay, like I said, helps to be able to spell, yeah? Right. Okay, so go and do some reading. Like I said before, it's always good to do some preliminary research and see what you can find out. And if you say, wow, you know, I read a couple of papers on this, 2 or 3 papers, and yeah, it looks pretty good. It looks like dark chocolate might actually have a beneficial effect on humans. Okie dokie. So then go back to your lab and say, I'm going to set up a hypothesis based on dark chocolate. And so that's what you're going to do. You're going to try to set up an experiment to test that. So you want to first figure out what you're going to be doing. An introduction is like a background. Now, this is not an abstract. Notice that abstract's not even listed here. So if you're familiar with scientific papers, abstract is like the true summary. You know, here's what I was doing. Here's what we tested. Here's what we found. It's not listed here because you're not really running the experiment. So the introduction is more of like background information. You know, here's what chocolate is. Here's what milk chocolate means. Here's what dark chocolate means. Here's what some past papers said that dark chocolate is beneficial. It's giving you background. It's really what the introduction is about. And then you're going to set up your procedure. And here's how we would have gone about testing something. If you wanted to do the 20 people idea, remember you're not testing anything. You can say like, you know, I would have had a control group of 10 people and an experimental group of 10 people. And in the control group, I did this. And in the experimental group, I did that. This is often known as methods and materials. They didn't write that word materials there, but you know, materials are slightly important. Like you're giving dark chocolate to one group and you're giving milk chocolate to the other group. That kind of idea. And then you would have collected data. You know, I was testing this and this is the kind of data I was getting back. Like maybe you would have done, I don't know, effects on cholesterol over the 6-month period, whatever it is. And was dark chocolate affecting that and therefore the cardiovascular issue? So you would have collected results. And then you would have tried to figure out a way to analyze it. Now here they're talking about that student's t-test I made reference of. You can then go and look up what a student's t-test. So you can do that, sure you can. Remember, you live in the information age. You can go, oh, I don't want that. News is not going to be helpful for you here. So you can go and find out, what is a student's t-test? What are some examples of it? Just go and do a little reading. You guys are adults, you're college students. You're expected to do things on your own to a certain degree. I'm here to answer questions, but I want you to try. By the way, that gets worse and worse, if I can put it that way, worse and worse, as you go to grad school. Undergrad, we're still there to help, but as you go through undergrad, it becomes more and more independent. When you go to your master's program, it's really independent, but the master's program is really designed to teach you how to do full, real research. And then once you get to your doctorate, it's like everything's on your own. And that makes sense because at that point, you have to be able to do independent research on your own. Decide how you're going to do it, why you're going to do it, what results mean. You got to do it on your own. It doesn't mean you can't ask questions. Of course you can. But they really want you to be independent so that when you graduate with your doctorate, you can now become a full-fledged independent researcher. That still means you probably work with a group of people. Sure, we don't do science in a vacuum, if I may say. But at this stage, the undergrad, we expect you to be able to take a couple steps on your own. So go and read. What is a student's t-test? What is it about? How do they employ it? And would that make sense in my experiment? There's no reason why you shouldn't. I mean, this is all about testing like food on human health. So use a student's t-test. Now, you can't actually analyze it. I am not expecting you in this class to actually sit down and calculate a student's T, only because this is all hypothetical. I'm not forcing you in any way, shape, or form. I don't even think you should. I'm telling you, don't do it. To go find 20 people and test on them. Don't do that. I don't want anything to happen to you or someone else. So just theoretically understand the student's T and how you apply it. You have no data here that you need to crunch. And then try to decide what kind of results you might have gotten. Like if I done a student T, I might have gotten these kind of results. I might have gotten these kind of results. And in my discussion at the end, then you could talk about that. Had I gotten these kind of results, here's what it would have meant. Had I gotten these kind of T-test results, here's what it would have meant. Just talk about it. And then you conclude, based on everything that's been done, dark chocolate looks like it might have had a beneficial effect. Or based on what's been done, maybe dark chocolate wouldn't have a beneficial effect. This is all hypothetical. I want you to get work on how to set up a scientific experiment. Observations, hypotheses, methods, materials, how you would have tested, what kind of results you would have gotten, and what conclusions might have meant. Remember, I'm not going to read this and say, oh my God, you thought that? No, of course not. I'm never going to do that to anybody. This is thought process. I want you to get more comfortable with this subject so that when you have this on your exam and there are questions on your exam about scientific method, you can answer the questions. You've grown in your understanding of what this procedure is and why we employ it so often in the sciences and even outside the sciences. I've known of people in other fields that have used the scientific method. Why not? It's a great method. So the rest of this really, once you get to like the t-test and on, has no bearing. You don't need to worry about that. There's nothing I'm requiring you to calculate because you're not collecting any data. Don't test anything for real. I can't emphasize that enough. Don't test anything for real. I'm not there to help you. I'm not there to control you. We're not doing this together in lab. So I don't want anything to ever happen. Stay safe at all costs. Stay safe at all costs. Now, once you've done all this, let's go back to homework. So let's go back to your syllabus. I think I closed it. That's not a problem. So go back to your folders, so files folder. Go to your syllabus link. Click on the syllabus. Okie dokie. Now, I just want to show you one more thing because it relates to the lab. Let's go to the homework section. And remember, I have a table of contents. If you're not sure where something is, like, oh, I can't find the homework, go here. Okay, it's on page 7. Right, let's go to page 7. I don't see the page number popping up, but there it is. So remember, 2 things are part of your homework. The the practice tests at the end of chapters. Do them and do them like I explained how to do them. And then the labs. So when you do the lab, now I gave a suggestion. This is just a suggestion to use a processing program like Microsoft Word to type it up. If you want to write it out on notebook paper, that's fine too. Just for any of the homework, the quizzes at the end you're required to do, that's the practice test, and the labs, like this first lab, you email it to me at this address. This is my HEC address, and it's due by this time. It is due by 11:59 p.m. on the day of the exam. Now, this is lab number 1, so that would relate to test number 1. Let's go right back one more time. I know I showed it to you earlier today. Let's go back to your tentative schedule. Right now, your first exam is on the 4th of October. And that means your homework for all the chapters, Basis of Nutrition, Evaluating Nutritional Information, Planning Nutritious Diets, Body Basics, and labs 1 and 2, the homework of them, it's all due by 11:59 p.m. on the 4th of October. Just get it together. I don't care if you use Word, I don't care if you typed it out, whatever it is, you wrote it on a notebook paper, I don't care, and email it to me by 11:59 p.m. via my HEC email, which again is in 2 places in your syllabus at least. So it is, of course, in the homework section, and it's right at the front of the syllabus. And you even have an email section in your syllabus, which has it. So again, there it is right there. Oh, right by the emails. There it is right there. And of course, at the front of your syllabus. So there's only 3 pages on your 3 places in your syllabus where you have my email address. You should have no problem finding my email address. And then get it to me by 11:59 on PM, mind you, on the day of the exam. So there you go. There is your first lab. If you have any questions, you're always welcome to ask me. If they're rather technical questions, remember, email is a bit of an impersonal medium. So I'll see it, I'll read it. Hopefully I read it and understand it how you want me to. I'll reply. Hopefully my reply makes sense. You know, it can kind of be like a back and forth sometimes, which is perfectly fine. There's nothing wrong with that. But if you think it's a little more complex and you want to get more direct information where you can real-time ask questions, don't forget to make a Teams appointment. And you're welcome to make a Teams appointment. I just had one today. So again, they happen all the time. So just go to that section in your syllabus where I talk about Microsoft Teams, send me an email, say, I'd like to make a Teams appointment. We'll work out a time that's amicable to us both, and then we'll have that Teams appointment. So beyond that, if you have any questions, as always, please, please, please feel free to let me know. And beyond that, I hope you're enjoying the class. I do have a few announcements coming your way. So keep an eye on that announcements tab. I tend to be, again, a rather communicative professor. So just let me know what's going on. Okay, beyond that, again, hope you guys are doing well. I hope you're so far enjoying the readings. And please let me know if anything comes up. Bye, everybody.